number of people, some of them are listed here. If we can have the next slide, please. You know, I hate it when people give Skype talks and conferences, and here I am to torture you with a bad connection. Roughly, what I'd like to do is put this in a broader context, given that this conference is aiming to cover a fairly broad arena. Talk about how technology is really what brings us where we are, and about a systematic approach to discovery. I will illustrate how time domain astronomy is growing in the optical using our own survey, Catalina real-time transit survey. And in the end, I'll make a few concluding comments. So, next slide, please. As you know, the astronomy has changed substantially over the last 20 years, and so has the rest of the world. And for the same reason, the information technology has been really changing everything, and it's producing an exponential growth in data volumes and data rates. So we have transitioned from the era of data poverty to enormous exponential data abundance. It also means that we can do interesting things that we couldn't do before. In the 1990s or 2000s, the digital detectors got us into the first generation of fully digital sky surveys, and astronomy entered into a terascale regime. But now the same progress in technology is bringing us into a petascale regime with synoptic sky surveys that cover sky again and again, and that opens a whole manner of interesting scientific possibilities. Next slide, please. So astronomy in time domain really is ill-defined in some sense, because it touches upon every single field of astronomy, astrophysics, or cosmology for that matter. And it's being powered by progressing information technology, which produces the data and also lets us extract knowledge from it. There are a number of synoptic sky surveys already operating and producing good science, and we are now embarking on the path to even bigger things with large synoptic survey telescoping opticals, per kilometer array radio, and so on. There is something for everyone in time domain astronomy, and so yeah, I said it's an obsolete term. It's like saying spectroscopic astronomy, but here it is. So it actually broadened our view of the universe in the sense that traditionally we're just observing the surface of the past light come. But as the time goes on, we speak this hypervolume in four-dimensional space-time, and so instead of just watching sources, we can now observe events which are spatio-temporal things, such as, say, supernova explosions. And the challenges that we're facing in real-time processing of these massive data streams are actually common to many other fields, and so that is a very important arena for many sciences, not just to us. Another important point is that sky surveys are discovering interesting things, but to really get most out of them, you have to follow them up, and this is where there are a lot of problems at this time. So next slide, please. So as we know, we're going into this era of massive panoramic cosmic cinematography, that we can actually watch the universe do things in front of our own very eyes, and that happens at all times. Scales from milliseconds through double time. And today, optical astronomy is certainly but radio astronomy is coming up strong, and that will be really a big data science. But the important point is that it's already happening now. You don't have to wait for these huge facilities. The next slide, please. The next slide, please. Well, let's start from the beginning. To put this in a broader context, and like many other things in astronomy, this started with Fritz Zwicky, who, among many other crazy and brilliant ideas, came up with what he called a morphological box, which nobody understood, and it's actually a poorly chosen name. Today we call this the parameter space. But basically what it meant is that if you carefully phrase any problem, and you can examine systematically all of the different variables and see what you can find in different portions of this parameter space. Zwicky actually used this to discover the ultra-compact dwarf galaxies, because there was a kind of galaxy morphology that actually wasn't anticipated until then. More recently, some of those have been rediscovered as so-called repeat galaxies by the people doing Galaxy Zoo, but never mind that. So next slide, please. Martin Harvey wrote a very interesting article and a book that looks to understand how our discovery is made in astronomy. And it boils down to progress in technology. As new technologies come about, we open new portions of the observable parameter space. Historically, that was new wavelength regimes, but now we observe everything from radio to gamma rays, and now we need to cosmic rays and gravitational waves. What's shown here is a plot of time resolution of different wavelengths, and different shaded areas indicate different time steps as shown here. And Harvey makes a good point that every time that we open a new portion of the observable parameter space, that we can measure something that we couldn't measure before, we tend to discover exciting new phenomena. And multi-wavelength astrophysics has plenty of examples for them. Next slide, please. So if we cast this in more modern terms, if you think about it, every astronomical observation carves out a hypervolume in the observable parameter space, which characterizes observations. We have certain area coverage, depth, wavelength, resolution, etc., etc. And circa 2000, when virtual observatory was coming online, it was clear that this was a good way to actually do systematic look at what we have observed and what we haven't observed. And one of the things that came up, how it happened. So this is parameter space of observations. This characterizes surveys themselves. Now, next slide, please. Once you measure things, you discover sources, measure some parameters, then you can actually start doing science. And so first you have parameter space of measurements. In some cases, those have physical meaning themselves, like colors, for example. This is a well-known example of how we find quasars in color space. But then the interesting things really start happening when you start folding in theoretical models and additional data, say distances. Then you can start looking in parameter space of physical parameters. And here is the example that's dear to my heart, a mental plane of our stellar systems. Actually, there are 3 of them. But that is populated by objects or events. And so casting things in this manner allows you to really start exploring systematically what's out there, what's available to your observations, and also to let you think what is that might be missing, because some portions of this parameter space remain hidden to you. Well, let me illustrate that with real scientific examples. So the next slide. I'll talk about Catalina Real-Time Transient Survey. I'll just give you a brief overview of it. It is a survey we're doing piggybacking on a search for Earth-crossing asteroids that's done by people at Lunar Planetary Lab in Arizona, and they're very good. They found 70% of all known near-Earth asteroids, including 2 that actually hit planet Earth. Fortunately, they weren't very big. So what we do is tap into their data stream, and they keep everything inside the solar system. We take everything outside the solar system and look for things that change. There used to be 3 telescopes, now there are 2. There may be more in the future. And the upshot is that this has now been going on for about 9 years and covers about 83% of the entire sky, with anywhere between 200 and 500 exposure to any given spot, more around the ecliptic. We avoid the galactic plane because of the crowding effects. And the way the survey operates is in a particular field, they take 4 images separated by 10 minutes in a given night, and they just march through the fields. So you get time baselines ranging from 10 minutes to now about 9 years in some quasi-logarithmic spacing. And it's just unprecedented amount of data for exploration of the time domain. One thing that we have decided from the beginning is to keep all of our data open. We publish all of the transient events in real time electronically, non-proprietary period whatsoever. And this is done because I think that it's irresponsible to do it otherwise. Any given group we can't do more than a couple percent of all science that's enabled by these surveys. And if we're talking about time domain, then 18 months later, it's not terribly useful. So I think we're hoping to introduce this open data philosophy, just like there is open source philosophy, that data can be open to the entire community immediately and enable more science than we can do ourselves. The next slide. So this just shows you a quick sampler of the kinds of light curves that have been observed, and they're all usual kinds of cosmic explosions and variable stars, where the stars are active galactic nuclei occur on all different time scales, again from minutes through many years, and we will also observe negative transients, things that actually get much dimmer, like the eclipses. The next slide. Don't bother reading the table. I always tell students never do use tables in their PowerPoint, but just look at the number that's circled in red. So to date, we have found and published just about 10,000 very strong transient events. And we define it in some suitable manner. It's a high amplitude, high significance. This is not all of the variable objects. If we actually turn a knob to find all statistically significant box variations, this will grow by more than an order of magnitude, and we can't even follow up these. So sometimes people with the LSSD talk about million or 10 million transient events per night. What they mean is every significant change in flux of anything. And out of those 10 to the 7 events per night, approximately 10 to the 7 will have no interest whatsoever, but a few thousand might. And it'll be interesting to find out which ones. So we publish this through a variety of electronic mechanisms, including NeoEvent, which we invented earlier for our previous survey Palomar Quest. We annotate them. There is a lot of interesting cellular infrastructure I don't want to go into. And handy numbers to remember is that when you look down to 20th magnitude or so, about 1 in a million sources detected will be transient. And there are roughly 1,000 transients, high amplitude ones from the sky at any given moment, down to about 20 magnitude. We find many of these again and again, of course, because the criterion is applied independently in all of the data. So that's the exciting real-time stuff, but actually there is more science to be done than purely archival sense. And the next slide, please. We now have essentially compiled 500 million light curves for objects down to about 20th magnitude or so, or about 80% of the sky. Here's just a quick sampler. And this is on the order of 100 billion data points. This is a completely unprecedented data set for studies of the time domain. It's open to you. We serve it, and it's now being served out of Anuka in India. If you actually take this data volume and put it to the Moore's law curve, by the time LSSD is operating, it will be exactly right. So in some sense, scaled by the Moore's law, Catalina survey today is the LSSD equivalent. And it's a good way that we can learn how to actually digest the data, how to find out what are the real challenges, and refine scientific strategies for the future. So just a quick walk through some of the science that we have done. Next slide, please. Well, we find a lot of supernovae, in fact, about 3,000 so far, and we published them all. So that's more than any other survey, including those that are designed to look for supernovae. But people who do those surveys tend to keep them to themselves, so that doesn't really help much anybody else. Among those, then inevitably we're going to find some very unusual ones, and we have repeatedly found extremely luminous supernovae, some of them potential reproduction, slow ones like this one that took over a year to reach the peak brightness as opposed to 2 weeks, and so on and so forth. The next slide shows a couple of particularly interesting results. The first one is that early on, we found that there's an ungodly number of supernovae that come from dwarf galaxies. Some of those dwarf galaxy hosts are barely more luminous than globular clusters. They're like SMC. And the specific supernova frequency in those is probably 3 to 4 orders of magnitude higher than normal galaxies. Now it's kind of hard to put a real number on this because we don't understand how many big wars there are. But one story behind this is that maybe these are coming to less of systems, and that might be populating the top end of the IMF, and therefore you instantly boost number of very massive stars that can explode. So in some sense, this is a local analog of the population tree, as best as we can tell. And similar effect was seen already with the gamma ray bursts. One supernova I like the best was this one that exploded in an active galaxy, Airline Secret 1. At first, we weren't sure what it was, and it wasn't type disruption effect. This was swallowed up in any of it with all wavelengths from radio to gamma rays. And when we took pictures with Hubble and with adaptive optics from the ground, instead of seeing two sources that actively put us in supernova, we only saw one, which meant that supernova exploded within 150 parsecs of the black hole, well inside the narrow-line region. And there is no sign of any star formation regions or dust or anything like that in HST images. If you think about it, this is like the worst possible place to massive stars, which incidentally, this was the most supernova I've ever seen. Except in the shielded regions, outer regions of the accretion disk. And they're shielded from the UV radiation, and they're also dynamically unstable. So it was predicted in the late 80s that there should be massive stars forming in the outer regions of the accretion disks, but nobody has seen it before because people who look for supernovae avoid active galactic nuclei like a plague. And yet, here's a new kind of phenomenon. The next slide shows some of the gamma ray burst afterglows. We're not specifically looking for them, but if we run a very simple spatiotemporal search on our data, every time that we could have seen an afterglow did. And that, I think, is an interesting, encouraging thing, because for identifications of the future gravitational wave events, or if they do have optical counterparts, even the current generation of synoptic sky surveys can find it, because the gravitational wave error boxes, or error regions, I should say, are expected to be in the region of numbers of hundreds of square degrees, but we already can cover up 2,000 or more square degrees per night. And so if these things that are above the detection limit, like 20 magnitude in this case, we'll see them. The next slide, please. Well, we'll find all manner of highly variable stars, more cataclysmic variables than anybody's ever found, and there are people who like to work on that. We also are the only survey that probes the minute time scales, and we see a lot of fast transits, changing in times of minutes. The great majority of those are young M dwarfs, or sometimes even brown dwarfs, with highly active chromospheres, but not necessarily all of them. So that may be an interesting arena in which we can explore and look for novel phenomena. Next slide. Well, again, just to bombard you with a variety of things, we see all kinds of highly variable stars, some young ones, core war stars, and so on. So there is, again, something for everyone in a data set like this. The next slide shows one of the early cute results, which is that we looked for eclipses of the white dwarfs, whiter potential planets. You know that the way with which we study the extrasolar planets now with Kepler and so on is through eclipses. Well, if you have an Earth-like planet crossing the sun like this, it's 10 to the -4 dip in the brightness. But if your star is the same size as your planet, then you can have 100% dip. And so we devised the criterion to look for such things, and sure enough, we found a whole bunch of them. So we found planets, Earth-like or Earth-sized planets around these semi-dead stars. This is an example of the kind of archival work that's enabled by this type of data. And of course, we look for variable stars. The next slide. Even with our first release of data with 100 million light curves, we had over 5 million variable star candidates, and among those, well, many are real, but we found about over 60,000 periodic ripples, which would also think of eclipsing binaries, and they span all manner of the variable stars, including some very unusual ones. Since then, we have expanded the analysis to full 500 million light curves, and the next slide shows that among all those variable stars, we found now 13 million variable stars candidates among the 23,000 new RRLI. So the variable star work is now no longer measured in tens or hundreds of stars per thousand, but in tens of thousands, or even more. So what do you do with these new RLI? Well, of course, you look for features in the galactic halo. So the next slide shows that we, in fact, have found a new tidal tail, which is called Gemini stream, and it reaches to over 100 kiloparsecs out. More of those will come up, I'm pretty sure, but it illustrates the power of purely archival study on something like a Catalina archive, and which is completely open to you, and God knows what other interesting things are hidden in there. The next slide. One of the early things that we did is we looked for the unsigned counterparts of the Fermi gamma ray sources using variability. Of the 1800 something Fermi gamma ray sources, only about 40% Fermi identified with some other objects, which is amazing. And at high latitudes, many of those will be blazars. Most blazars are not briefly cataloged, so we simply looked for light curves of everything inside Fermi gamma ray ellipses. And invariably, most variable object is a blazar, which is probably coming from the gamma ray source. So this shows an interesting way to do optical identifications through positional matching and colors and so on. Here we use variability alone to identify sources found in a different wavelength regime. Now, turning your attention to quasars, next slide. We have the data set to study variability of quasars on timescales up to about a decade or more if we add additional data. And one of the first things to ask is what can variability to discover quasars in a manner that's completely independent of their spectral energy distributions, which we can also combine with cores such as those from LISA satellite. There are about 1.3 million quasar candidates now known, almost all of them Hubble selected, and almost all of them from SLAM. We think that using our techniques, we can probably find another billion or so quasars over the 80% of the sky. Not to go through any details, but we found new ways of characterizing the variability. And the next slide shows that we actually do find quasars, and success rate is over 80% so far. I think it will go even higher yet. And so we can have a much more complete and richer set of quasars, and then study their variability as a function of other physical properties, different regimes, and so on. One of the things that came up out of the study, and shown on the next slide, is the existence of a characteristic time scale for stochastic variability of quasars, which was hinted at before in the X-rays, but was never really established in the optical. However, when you have light periods of 250,000 of spectroscopically confirmed quasars, then you can certainly do things that you otherwise simply would not be able to do. The physical reason why there is this time scale, which is about 50 days in the rest rate, but it and that correlates with luminosity, is not very clear. One possibility is that has to do with the diffusion timescale accretion, but we don't really get, so this work still in progress. But since then, we made an even more exciting discovery, which I'll share with you today, and this is the first time it's really publicly announced, and it's shown on the next slide. that we deployed new ways of looking for periodic signals, and we found, I think, first convincing evidence for periodic variability in quasars. The first case is shown here, P1302-1, has a rest-frame period of about 4 years, and we have found another 20 or so candidates. This is now a paper in press in Nature. In other words, about 1 in 10,000 quasars belongs to this category. That, remarkably enough, is exactly what theory predicts for the spin spiral of supermassive black holes, because these things are well inside the central parsec. There are milliparsec separations. So I think that opens up another exciting area of study. It will be a while before these two merge and send vertical gravitational waves. But there is no other way in which we can possibly probe supermassive black hole binaries on milliparsec separations. So the next slide, I think I've been talking about optical astronomy, but really radio astronomy in time domain is where all the action is going to be, and it already is with SK precursors. Both in Australia and South Africa, and as you probably know, there was the exciting discovery of millisecond radio transmittents, and we still don't know what causes them. It's a wonderful example of how you can discover a previously unknown phenomenon when you open a portion of the parameter space. With all of the work done in the optical, sad to say, we actually haven't found any fundamentally new phenomena. We have found many interesting things, or extremely unusual, rare subsets of known kinds of things like supernovae or whatever, but we haven't found something that's genuinely absolutely new thing, like gamma ray bursts were absolutely new thing at one point. Now radio astronomers have just begun and they found this fast radio burst. So radio is a thing where a lot of excitement will happen in the future. Next slide. Here is what I think is the single most important challenge for the time domain astronomy, which is rapid characterization and classification of transits. When you discover one of those things, it looks like a star that's a little brighter now. It used to be, but wasn't before. And that's all we know about it. It can be completely different things. Some flaring or a mystic jet on the other side of the universe, cosmic explosion. But the different physical phenomena look exactly the same. And some are more interesting than others, so you'd like to know as quickly as you can which ones are interesting enough so you can spend valuable time with them. And that turns out to be an extremely difficult thing to do. This is, I think, the single most critical need for further progress in this field. We've been at this for a long time. The next slide shows schematically what we really are trying to build. So essentially, time domain astronomy really is a microcosm of virtual observatory done in real time. The ingest event streams it pull all the archival information we have from the connected archives. You have to feed that into some machine learning machinery and come up with likelihoods that any given event belongs to some category of matter. Use that to decide probabilities for the follow-up with more expensive facilities, feed the data back, iterate all that in real time. The reasons why this is very difficult to do is that for every event you measure different things. And the data are very heterogeneous, they're very sparse. A lot of important information is contextual, what's around it, what happened there before, and so on. And this turns out to be a very interesting, difficult problem for machine learning people. We've been working on this more or less for almost 10 years now. And some progress has been made, and this can be a whole talk in of itself. But I just wanted to make you aware that this is a very important thing that several groups are now working on. And the next slide is sort of the direct follow-up to what I meant earlier. In order to extract science from these things, you usually need to get some follow-up observations, spectroscopy in particular, and this is difficult. because we just simply don't have enough telescope time to do so. Even today, with these smaller surveys like Eta transient factor stars, we follow up at most a few percent of all high amplitude transits. The rest of them are just popping on the ground. And there may be exciting things there that we're missing because we don't have enough spectroscopic time. Now, this is going to get much worse, by orders of magnitude worse, with the next generation of sky surveys. And that means that we absolutely must learn how to prioritize and triage events and which ones will be worthy of follow and when. Now, most of the telescopes and most spectrometers and big telescopes are built to study galaxy evolution, highly multiplexed and so on, whereas in time domain, you want to take one object at a time quickly and go quickly to different parts of the sky. So this, I think, is where it would be a good idea for this community to get its act together and do coordinated observing, both in the optical, different cases, but also between different wavelengths. Because if radio astronomers think that optical astronomers will stop in order to follow up radio transients, well, they have a second thing coming. The best thing to do is to do mutual follow-up by co-observing at different wavelengths. That way, maybe we can already have built-in follow-up for many of these events. The next slide is just to make a few concluding remarks to emphasize some of the things that I already said. I think the most important lesson is that time domain astronomy is here now. This is the golden era of time domain astronomy. You do not need to wait for LSST or SKA. This is the time where we're actually discovering interesting things. And there's plenty of data. People like to get their own, but here is the free data stream. Catalina, if something is free, it doesn't mean it's worthless. It actually is very useful, as I think I illustrated. And there is plenty of science yet to be done with what we have. The second important takeaway point is that time domain astronomy is astronomy of telescope computational systems. It is microcosm virtual observatory, and it really requires a strong inside infrastructure where you have to deploy just database, data access, and data discovery means, but all manner of machine intelligence and classification tools to figure out what they find. This is a good thing because maybe we can actually do something for the society, because similar problems are now arising in a variety of other fields. And if we come up with some good tools and techniques, then maybe we'll use somewhere else. And we're already working with biologists in trying to use some of the stuff that we've done for astronomy applied in water genomics and cancer research. So the surveys today are the testbeds and precursors of the big things to come, and the science is here now. If you'd like to work with us with Catalina 2 survey, please get in touch and we can discuss that as well. And so if you show the last slide, I'll be happy to take any questions.
I think we have the time for one question. Of course, there are more. Okay, Daniel Thomas wants to ask. I don't know if you can hear, in case I repeat it.
Hello. I think the discovery of the supernova close to the accreting black hole is really exciting. Can you just say more about this? Do you think this has only been found now because you are exploring a new parameter space in the type of experiment, or whether it's just so rare that you needed large data sets?
Unfortunately, the scout works like Alexander Graham Bell's telephone. I didn't understand anything. So, Nicola, can you repeat the question, please?
Okay. So, I was asking about the supernovae close to the black hole. He said it is something that is you find because you are exploring a parameter space or something that you expect to observe more often.
Yeah, but that's just a rare event. And
it's just a rare event, yes. So good, just by chance.
Well, yes and both. These clearly are very rare events, but we dug through our archives and we found other cases of active galaxies where there was such a light curve. Now, of course, it's too late now because the supernova's gone. If that's what it was, we also title disruption events, but we're on the lookout to find more. These events are rare because we're talking about extremely small volume, come to think of it, and we were just plain lucky to see the first one that we saw. But I think it is something an exciting pointer to things that you can find once you have such a dense sampling with a parameter space.
Questions? If not, considering the situation, I think we have all to thank you, George, again.
I wish I was there.
Okay. Okay, next time. So, next speaker. Thank you very much, George.
Okay, our next speaker is Roberto Ragazzoni. He's going to talk about Plato 2, a survey for close-by exocurrent systems.
Who's stuck? Okay. Okay, great. Thank you. Thank you. Okay, so first of all, I'm speaking about Plant 2. This talk was supposed to be given by Isabella Pagano, that unfortunately have an obligation exactly for this project in Berlin, so he could not come here. So it's a pleasure for me anyway to speak here about Plato on behalf of a large amount of people involved in it, Gianpaolo among the others here. And it's a pleasure, of course, to be here in front of such an audience with Massimo as a friend, but we will have tomorrow more fun with VST, which I'm more involved in, and to Yannick, that has been I'd say, a great competitor of this mission in the previous M1 and 2 selections. Okay, so said that, let me remind what is Plato. Plato is a medium-sized mission. You know that the ESA defines the mission by the amount of money. This makes slightly difference on the kind of mission depending which kind of launcher. In this case, the launcher is a relatively cheap Soyuz from Kourou, the same that has been used by Samantha, well, at least the first part. It will go to the L2 orbit, so far away from the Earth, like Gaia, and it's supposed to operate for 6 years. And it's supposed to be launched in about 2024, basically. And the primary goal is to make a survey of planets around stars, such that it is possible to determine for each of these planets the radius, the mass, the age, with unprecedented accuracy. So it will open another domain with respect, for example, for Kepler, and especially, of course, in the habitable zone of solar-like stars, and not only. And this basically means that the aim is to look for planets around bright stars. This is the key point about here. If you look, for example, for Kepler made a great work. It's made statistics, but most of the, so we know that there are a lot of planets of Earth's mass size, and we know from radial velocity other informations, but the common between the two is more rare to find, just because Kepler finds a lot of relatively faint star that was not able to determine, to make any follow-up with the radial velocity. We will come back on this, also following the Jorgowski talk, very interesting. Okay. Of course, to find the size and the mass of the planets from the two different techniques from transit and from radial velocity will allow to make the determination of the density that will be crucial to understand if it is rock-like planets or gaseous-like planets, and to try at least to get a first guess of which are of the structure, internal structure of the planets. There will be, of course, a number of interest in what is called the habitable zone, okay? That, of course, depends upon the kind of the stars, or the class of the stars. And basically, if today you look for planets, in which it is known from both the radial velocity and from the transit. So we know both the size and the mass, hence the density of planets in the habitable zone. We basically found none. So this, of course, is an issue that a lot of people are thinking about it. So there is a number of missions that are ongoing. Kepler, after the problem of the gyros, has been revitalized in what's called K2. There will be another mission which we are involved with, Cheops, that is basically a follow-up of specific planets for which radial velocity is known. There is TESS, that is, however, a mission that will observe, the whole sky, but only with a full time of 1 month per each part of the sky. Only a small fraction of the sky will be observed for a single year. And Plato will observe basically for several years a large fraction of the sky. So this will be what we expect from TESS, Cheops, and K2. So basically to explore this area of planets that are a period of the order of the one of Mercury or faster. We have to wait for Plato to arrive to explore the whole parameter space and to find stars in the habitable zone twins of the Earth. So this is the jump in magnitude that we need. We need a jump in magnitude of about 7 magnitude to go to brightest star. And this basically means, this is a short movie that shows, this is Kepler, and because of the probability of the transit that is low, you need to observe a large number of stars. And the way Kepler do this is just looking deeper and deeper. So most of the stars are faint, just to have an example of 1,000 stars. And so in Plato, the closest and apparently brightest star, to observe the same amount, the only way to do this is to have a much larger field of view. So Kepler goes deep into a relatively small region, and Plato will observe a very large region with bright star. How much bright? It is from magnitude 4 to 11 for a complete characterization, and then there will be up to 13 magnitude between 12 to 30 for just the detection planets of Earth size. That will be, however, hard to make any follow-up for this, but just to have the statistics. And up to magnitude 16, we will be detected larger planets and probably with no radial velocity, just to improve the statistics. These are again the numbers of the precision that we want to see. Asteroseismology is going to be used to characterize the age and the size of the star, because actually transit gives a ratio between the size of the star and the size of the planet, and the age will be another parameter that will be useful to have an idea of the status of the planet. So now let's switch to how this is done. So the key point here is to observe a very large field of view. We're speaking of several tens of degrees, more than any Schmidt camera that we know on the ground. So this usually requires to make a plate scale such to provide on existing detectors a very large scale. This makes an optics that is impossibly over fast. And so the idea is just basically to break up the telescope into a number of smaller telescopes, each of one at its CCD. This also allows to have a much larger full well of the CCD, because you basically pile up the full well of the several CCDs. This is the optics of one of the elements of the telescopes, that is about 40 degrees of field of view. And furthermore, these are not, there is an array of about 34 telescopes, and in groups of 8, they are not looking exactly in the same direction. They're not pointing all in the same direction, but they are divided in 8 groups with a slight angle between each others, such that the first group of 8 will observe basically this region of the sky, the second group of 8 will observe this region of the sky, and so on. So in the very center, there will be 32 telescopes simultaneously looking for much fainter or higher precision stars for relatively for intermediate brightness of the star, and for the brightest star, like for the fourth magnitude star, it is possible to achieve the error in measurements also in this region with only a smaller number of telescope. And you see the field of view is 60 degrees, so it's a very large field of view actually. This is another movie that just again visualize this. So these are the 34 telescopes. These are images that are looking the same, and then the angle open. And the pattern of observation in the sky has also a fourfold symmetry, because for practical reasons the telescope will have to rotate every 3 months by 90 degrees. And so in this way, the same star will be observed by different telescopes and different CCDs, but will always the same pattern. The field of view I told you is of the order of 60 degrees. This is very similar to the central area of the eye. So there is a large number of CCDs on the focal plane. Each focal plane is about an 8K by 8K equivalent CCD. And if you imagine to have all the lenses of the cameras grouped together, you have the equivalent of about a little less than 1.2 meter telescope in Asiagon. And if you look to the CCD, that again is roughly the same amount of CCDs involved in Gaia. Here is this show now just the CCD and the front lens, and now isolate the CCDs. And if you group all the CCDs for all the camera together, you basically get something of the order 1 meter. So it's like having an eye with a 1.2 meter diameter of the lens, and the retina of about 1 square meter inside, to get an idea of the arrangement. There's been, as is usual in the ESA style, there's been 2 competitive call to industry to how to accommodate this. One is made by Alenia Space, in which is this octagonal shape with the telescopes arranged in this way. So this is about several meters in diameter, and this acts not only as a solar panel, but also a sun shield to avoid that the light of the sun can reduce the performances of this camera. And the other was being by Astrium, in which this was nicknamed Toblerone, if anyone from Italy is aware of what this means, okay? In which the telescopes are located in a single plane. So each has different characteristics, because of course not all the telescopes have exactly the same performances because of stray light, because of vicinity of the others, and things like that. This is not only papers, not only a piece of paper drawing on the papers, but we build a real prototype of one of the telescope to demonstrate that it was doable, that it survives the space, and it is possible to align within a week, because the problem is to build 34 of this. There is also a lens in calcium chloride that should be the biggest one that will fly, and this has been made several of this, and has been thermally cycled in vacuum. So the whole camera has been placed in a cryo vacuum chamber to test the performance, its characteristics in space. And another issue that, however, is still under debate. I mean, this is exactly what was foreseen at Plato 1, but was to make 2 long pointings of about 2 to 3 years. So the idea of 3 years is to have 3 transits for Earth, for twins of the solar system Earth case. So there are 2 areas, one on the north and one on the south, in order to have follow-up in both the hemisphere. And then a certain number of step phases, which from 2 to 5 months will be observed. And if you pile up, because of the larger field of view, all this, you get up that the whole mission should look for about 50% of the sky. However, with a time domain that will be slightly different. Which is the numbers that are involved in this. The number of stars that are going to be observed is huge. These are the numbers, so it's 10 of thousands for the one with 34 parts per million of level of noise, and with the reduced performance in photometry, the number will approach 1 million at the very end of the mission. So it's a huge number of light curves, of course, that will have, some of this will lead to detection of Earth-sized planet. We know now from Kepler data that the assumption that each star has one planet is a rough but very good approximation. And of course, now we have to give our contribution to the follow-up crisis that was mentioned by Jorgowski, because of course this will require several nights on telescopes of 2 meter plus, on 4 meter plus, and 8 meter plus, and of course there are ongoing strong discussions to to be sure that this will be available. And in some very specific case, we probably need something like ELT class. I mean, okay, let's see if we know. I mean, so it's not an unreasonable allocation of time, of course. And the number of years of planets that one can expect, these are the kind of numbers that are going to be, I mean, suppressed by the reality. But the order of magnitude you see here are planets of 1 year and about 1 year period, and about 1 Earth mass is about 30. So even if you add a certain variance here, it's likely to have several anything. So this is one of the pictures in 2011 of the Plato involved communities that, of course, is growing, especially because it's being selected. And let me recall that there is a science conference about Plato soon, in the beginning of December in Taormina, and this is open to all the community, both the astroseismological and the planetary one. And there is the website, but I think this kind of thing now you can easily Google. And so let me finish just showing while I finish the profile of the mission with Plato that in L2 around the sun every 3 months rotate by 90 degrees and observe one spot on the north and one on the south. Thanks a lot.
Thank you, Roberto. We have a moment for a question or two. Yes, Mike.
So the Kepler mission, if I remember correctly, excuse me for my ignorance if not, doesn't download, images from this CCDs. They have integration apertures, 100,000 of them are so defined on board, and the total flux in each of those apertures is what comes down to the data stream. What's the plan here?
Okay.
We've got a lot of pixels.
Okay, first of all, okay, the baseline was that it's similar. So occasionally you send down what are called imagette. So just a small fraction, but just to decide which are the mask, and you send down the flux and the centroid. That is just a sort of to understand if something is changing because of variations the telescope radars. And so it's now the point, for example, for TESS, that is to a certain extent is an intermediate mission between Kepler and Plato. They are thinking to send the whole frame every half an hour, if I remember correctly. We had a discussion with Dave Latham just a few days ago about this. And for Plato, this is not the baseline. However, I mean, because in the meantime the technology changes, there is an option that is being studied by ESA to change the data link from the spacecraft to the ground. So the baseline is just to send photometry and centroid, and occasionally the imagettes or the full frames for, let's say, housekeeping purposes. But this could be modified by the implementation.
Okay, another question? Okay, well, thank you, Glenn. Okay, next speaker is Gianpaolo Cuppi. He's going to talk to us about the trajectory surveys of galactic quantum clusters.
E io mi devo mettere qui. It's 5 minutes. Okay, good morning. So let's change topic again. I will present you some results that we have from different surveys, mainly based on HST of galactic globular clusters. Usually, I like to start my talk showing this columnar diagram because this is, in a way, the best that we could have at the end of the 80s, beginning of the 90s, in terms of main sequence of a typical globular cluster is M30. And you should take it very seriously, first because this is the best product of my thesis, and second because Massimo Capaccioli was my supervisor. And I always have to thank him for introducing me to the fascinating world of subclusters and stellar populations and star clusters. Okay, so then we had HST. Things rapidly improved in terms of our capability to study globular clusters. Here you see what's typical with the typical main sequence of a globular cluster that we could get with HST and with the best ground-based facilities. This kind of columnar diagram is a sort of example of what's at the time was considered to be the typical stellar population of a globular cluster, which was considered a simple stellar population in terms that you see that you don't see much dispersion in the main sequence. In practice, at that time, we were thinking that all the dispersion was due just to automatic errors. You don't see, this means that you don't have a large dispersion in iron at least, or heavy elements. And you see that there is a small dispersion also at the level of the turnoff, which implies that, the idea of objects forming from the same cloud, the same age, at the same time, same chemical composition, and so on. Things change rapidly. This is the picture that we have of the same cluster that I showed you before, and this is 1697 at the moment, particularly when we observe these clusters using ultraviolet filters. Indeed, particularly with the advent of WC3 with HST, really our picture of the stellar population in globular clusters has radically changed. Okay, the fact that there was not everything was so simple and was clear since the 70s, thanks to the work also of Ken and many others, because it was clear since then that there were anomalous, at least in terms of light elements, there was a dispersion in some cluster of their contents. The problem is that apart from a few people, most of these, of these variance in metal content in globular cluster was considered just a sort of anomaly. There was no, a picture that was able to explain why we were observing these variations in chemical content. Then, with the capability of multi-fiber spectroscopy, people started to do more systematic surveys of the chemical content of globular cluster. And one thing that came clearer and clearer was that these anomalies indeed were not really anomalies, they were correlations. Like, for example, as you can see here, the anti-correlation between sodium and oxygen. And this anti-correlation was in some way puzzling because the fact that you have stars with high sodium content and low oxygen content was implying that the material from which these stars were formed should have been gone through hot hydrogen burning in the core of these stars. And because these kind of anti-correlations are present also for main sequence stars, it was clear that this material should come from outside, and those stars should have been formed from this kind of material, because main sequence stars today are not going through the CNO. The hydrogen burning in the core of these stars is not through the CNO side. Well, just a brief historical remind. There was one cluster for which it was clear since, I would say, end of 70s, beginning of the 80s, that also the iron was not constant. That stars in this cluster had different iron contents. And as you can see here, with a large spread in iron content, and it started to be clear that also the red giant branch, this is the second half of the 90s, was split in many different branches, and you could link very well the differences in iron content of these stars and their location on the columnar diagram. So, in a sense, it could have, it could have been somehow expected that also the main sequence could show something like that. And indeed, this is what was clear since to us since the, let's say, 97, 98, but we never published this main sequence for a very simple reason. Because if you see, most of the stars here are on the red part of the sequence, while most of the stars in Omega Centauri are just metal blue. So you would expect to have most of the stars on the blue part of the main sequence, according to what we learned in our first class of astronomy. And the fact that this was not corresponding to the contribution metallicity was puzzling us a lot. But at the end, when the ACS came in, this diagram was clear. In different regions, it was clear that the main sequence of Omega Centauri was split at least into two sequences. At that point, we went also to VLT, and this is the combination of 200 hours of photon collection for a blue main sequence star and this for a red main sequence stars with VLT. Well, what became clear at that moment was that indeed the bluer sequence was also more metal rich. Again, I repeat, this was something very, very unexpected in a sense. And the only way that we have even today to explain the photometric and the spectroscopic properties of the main sequences of Omega Centauri is to admit that the blue sequence, which is also, as I said, more metal rich, is also extremely overabundant in helium. 0.40 in terms of Y, 0.39, okay, with a small error, as you can see, which implies that almost 40% of the mass of these stars are helium, okay? And this is not easy to explain and to produce. This is the present picture that we have now of Omega Centauri, where you see there is a much larger complexity in the stellar populations. In this cluster, you see at least 3 main sequences, but there are more, and we counted up to 11 subgiant branches and red giant branches. Again, thanks to the possibility of observing ultraviolet distance. Okay, Omega Centauri is a sort of special case, the only one with a huge dispersion in iron content. Not the only one, as we know now, with dispersion in iron content, but for sure the one with the largest dispersion in iron content. So we went to observe other clusters, and the second one that we picked up for many reasons was NGC 2808. And again, we see that the main sequence of this cluster is split in at least 3 sequences. I will show you later on the present picture that we have of this polymer diagram. But anyway, at that time it was clear there were at least 3 main sequences. And because there was no dispersion, it was known from spectroscopy that there is no dispersion in iron content among the stars in this cluster, again, the only way that you have to explain these 2 bluer sequences is to assume that they have an helium overabundance, 0.35, 0.40. Something that was predicted, for example, by Francesco D'Antona also in order to explain the horizontal branch of this object. Before going on, there are many possible scenarios for multiple stellar population. One important thing that we have to note, which comes in particular from photometry, is that these sequences are discrete sequences. There is not a real spread in the stars, in the main sequence, in the red giant branches. There are discrete sequences that you can distinguish very well. And if you take, you have many possible possibilities, to explain the origin, at least the origin of the material that has created the second, the third population, or even more that we have in these clusters. But if you consider the discrete sequences, you have to exclude a few of them. If you consider that for most clusters there is also no dispersion in iron, there are very few possibilities that remains. And one of these, I'm not saying that this is an explanation, but I understand that the only explanation we have in this moment, which is able to take into account the columnar diagrams and the results that we have from spectroscopy, is to assume that you have more than one generation of star, with the second or following generation forming from material that is being ejected by intermediate mass asymptotic giant branch stars. This kind of models predict that the second generation of stars should form mainly in the center of the cluster. And indeed, when we go to observe the ratio of, for example, the blue and the main sequence in 47 Take and Omega Centauri, which are 2 very massive clusters with the long relaxation time. So stars have not had the time to mix because of energy equipartition. Indeed, we see that there is a gradient with the bluest main sequence. Talking about what we have seen till now, which we associate with the second generation of stars, are really more concentrated than the redder one. The AGB model predicts also other things. It's able to predict the overabundance in helium, because AGB has an ejected material that has been gone through the hydrogen burning. And also able to predict, for example, the sodium-oxygen correlation that I've shown you, and many other chemical properties of these stars. Now, if we work on why ultraviolet images are so important in order to distinguish different cell populations in globular clusters. Well, there are at least two effects we have to take into account. The first one is the effect in temperature due to overabundance of helium. Stars which are enhanced in helium are also have also higher temperature, which means they are bluer, as we have seen also in the case of Omega Centauri and NGC 2808. And this is easier to see if we go in the optical, we use optical bands. Now, this is a complicated view. I don't want to enter into technical details. We don't have time. I just want to show you that this is, the wavelength from 2500 to 4500. These are the three main UV filters that you can use with HST. This is close to the usual B band. And you see that these filters are mapping OH, NH, ACN, CH, and so bands. And if we follow, for example, the idea of the intermediate masses in generation stars, we expect that first generation stars have the normal carbon, carbon, oxygen, and nitrogen, while second generation stars should be carbon and oxygen pool and nitrogen rich. If you put everything together, and these are synthetic spectra, then you compare spectra with these properties, you find out that the UV filters are very capable to measure the differences in carbon, oxygen, and nitrogen between the two stellar generations. You expect to have a blue, the first generation as a bluer F336 minus 814 color, and redder 275 minus 336W. And if you combine these colors, you can even better distinguish stars which have a different carbon, oxygen, and nitrogen content. This is an example of 47 TAC. Now we show you, here you have the main sequence. Here you have a two-color diagram combining the colors that I have shown you before. And you see that you can clearly distinguish two main sequences. You can do the same thing at the level of the subgiant branch. You can do the same thing at the level of the red giant branch and of the horizontal branch. And afterward, you have this very nice picture where you have separated the two populations very well from the lower part of the main sequence up to the horizontal branch. You can do even better. This is, for example, NGC 6752, paper that we published a couple of years ago. In this case, using the same kind of, playing the same kind of game. In this case, we could distinguish three different stellar populations. But for this cluster, there were observations of the main sequence. They did observations in 5 different photometric bands. So once using the two color diagrams, we could separate, okay, as in 47 TAC, all the different main sequences. You can trace all these sequences in all colors, and you can calculate the difference in color of the different populations in the main sequence. Then you do some modeling, and at the end, the nice result is that you can have an estimate of the helium content. Okay, this was a simple case because of the large number of photometric bands that we had, and because there were many observations, so we could give it to the single population the appropriate chemistry, the appropriate carbon, nitrogen, so on content, and at the end, using the photometry, using the difference in color among the main sequences, we could have an estimate of the helium content. And I could show you many other examples like this. So at the end, last year, we decided to apply HST for a large survey, for a large UV survey, which was closely linked to a previous optical survey. So you observe, we observe it now because the survey is almost completed, almost all observations have been collected. We're using, we're covering the same field for which in a previous treasury program we collected 606 and 814 optical band images, and we added the UV and V images for 47 clusters, plus there were other 13 clusters in the archive. So now we have for more than 1/3 of the globular clusters at least 5-band photometry to trace the different stellar populations. Here you see a few examples, just to show you. And believe me, the conclusion is that all the clusters in our survey are showing in some way the presence of multiple stellar populations. So, as in the case of the sodium-oxygen correlation, for example, for which in practice all clusters that have sodium and oxygen observations are showing the sodium-oxygen correlation, which I said is by itself telling us that there is more than one stellar population in the cluster. I repeat also the photometry is telling us that all globular clusters are hosting more than one stellar population. This data reduction has been done mainly by Antonino Minone, and now he's working on Stromlo, and he really is doing a great work in trying to extract all the single stellar populations from this survey. And when you go in details, when you have that fantastic database, you see that things are even more complicated. Thank you. In the case, for example, of M2, which is one of the clusters of the survey, as a paper that has been recently accepted for multi-analysis. In the case of M2, we could distinguish 3 main stellar populations. Forget about the meaning of these labels. These are simply combinations of the ultraviolet and blue and in optical colors. We could distinguish 4 main stellar populations. And the nice thing is that in this case, we could correlate these populations with their chemical content. And indeed, we can map the differences in chemical content, like elements and iron. This is one of the cases where there is also small iron dispersion. And looking in more details, this group of stars, we could find that that group of stars could be separated into 3 different, again, stellar populations. Indeed 4, because probably there is something more, but at least 3 stellar populations. And again, we could connect the photometric evidence with the spectroscopic chemical content which comes from spectroscopy. So in the case of M2, we have at least 7 different groups of stars in the same cluster. Then I'm working on NDC 2808, which is the one that I've shown you, the second columnar diagram that I've shown you, where we have identified back in 2007 3 stellar populations. And in this case, there are again at least 7 stellar populations, but we're still working on this cluster. Couple of things that I wanted to add. As I said, most of the clusters do not show dispersion in iron content, but some do. For example, M2 is one of the clusters that has a small difference in iron content. In this plot, you have sodium here you have iron, again iron, and other elements. Here you have aluminum and thereby. I want to point out the similarity in the dispersion of iron and in the dispersion of sodium between M2, which is the cluster with the 7 stellar populations that I showed you before, and the core of the Sagittarius galaxy. The core of the Sagittarius galaxy has the nucleus of the galaxy and a globular cluster. You know that the Sagittarius galaxy is on the verge to be completely disrupted by our galaxy. In practice, the entire galaxy will be soon dispersed in the field, and what will remain will be just the nucleus plus the globular cluster. And this is the color diagram of M54. The chemistry of M54 plus Sagittarius is very similar to M2. But for example, the color diagram of M54 is very similar to the color diagram of another cluster, Omega Centauri, which shows a large dispersion in iron. So it's tempting to say that at least these clusters, which show also a dispersion in iron content, may be just what remains of the nucleus of a much larger system, of the dwarf galaxy, which has been destroyed, and now we are just observing the central part of what remains of that event. So at the moment, the picture that we have is that there are globular clusters which look normal, and by this I just mean clusters that do not show any variation in iron content, but they do show variation in light elements like sodium, oxygen, and so on, as I said before. And some anomalous globular cluster which shows the same thing, plus also dispersion in iron. Now the question is, in particular for these clusters, are these clusters the remnant of the disrupted dwarf galaxy? And if so, how massive was the dwarf galaxy in the past? We do have a problem here. And I don't think I have time, but there is a problem with the mass of the progenitors of these objects. And again, are these just the remnants of dwarf galaxies? So quickly summarizing, globular clusters are not simple stellar systems, and they do not also simple stellar populations. Multiple stellar populations are in practice present in all clusters that we have observed up to now. Multiple stellar populations imply the presence of stars with material that has already gone through auto-hydrogen burning. For a few clusters, we see not only a variation in some light elements, but also a dispersion in iron. In any case, at the moment, the most plausible explanation for the presence of multiple populations in globular clusters is implies the presence of multiple stellar generations. And this implies also that in any case, in order to have enough material to form a second generation, a third generation of stars, in any case, these objects must have been much more massive in the past. How much is still debated. Thank you.
Thank you, Jean-Paul. Any questions? Yes.
So this is very interesting because we can learn about galaxies. And so I wanted to ask if this sequence of, I have many questions, but it seems that in the for the very metal poor clusters, -2 at the average, the most metal poor in the yellow, are these sequences also seen? Do you think there is a metallicity cut about which you start to have multiple generations in terms of total metallicity, not iron, just Z average? What is the time difference between the main sequences, which you approximate as a series of bursts? And do you see any difference in the initial mass function of these main sequences?
Okay. First, I don't know how to answer the first question, because, as I said, we see multiple populations in all clusters, including very metal-poor clusters and very metal-rich clusters. So I don't know if, I don't see a cut in this moment, okay? I have no evidence that there is a cut in metallicity, say, for more metal-poor clusters, there is no multiple generation or so. Even 6397 or M30, and these clusters are showing, all of them are showing multiple populations, okay? Now, if, as I was trying to say at the end, if the origin of this multiple population is the same for all of them or not, it's something that we need to understand better. But there is no cut in metallicity, at least among globular clusters, stellar populations. Second question was on?
The age sequence.
Okay. Difficult to answer. Okay, in the case of galactic globular clusters, we don't have any evidence in this moment of an age difference. Okay, in the sense, I mean, among the different stars, in the sense that, for example, if the intermediate AGB scenario is correct, what you would expect, okay, is that the second generation is forming after 100, 200 million years, not more than that, and you cannot measure. Even with this very nice HST images, you cannot measure 100, 200 million years. We tried with Antonino very hard in the case of a cluster that we are working on, but we can say that the difference in age is less than, let's say, 300 million years. But it's not possible to measure difference in age. On the other hand, there is another work that we did on intermediate age, LMC clusters, where there seems to be a dispersion or even multiple turn-offs for 2/3 of them at least. Okay, if you interpret this in terms of difference in age, is of the order of 200-300 million years. But you can interpret it in terms of rotation, many other things. Again, this is a debated result. But if you interpret the dispersion in the turn-offs, the difference in age is of the order of 200-300 million years. Regarding the mass function, okay, there is a paper that we published in 2808. There seems to be a slight difference in mass function, but it's a very, very hard work to do. We want to do that, but there is not much at the moment.
So, in thinking about much more massive galaxies that are not passively evolving, one of the arguments that comes up repeatedly is star formation versus the assembly of the stellar system. Stars are being formed in individual populations and halos that merge. What is the evidence, or is there any, that if there are multiple stellar populations in the globular cluster, that those all formed in the same place?
Okay, the evidence is that I mean, the evidence is just in what you find. I mean, okay, for example, in the case of M54. Let's take M54 Sagittarius Galaxy. We don't know if the globular clusters were formed. I mean, the M54 itself has formed just in the nucleus of the galaxy where it is, or it came in for a dynamic evolution, blah, blah. Okay? But I found it difficult to link what we see in globular clusters now on, I mean, I found it difficult to say everything has been produced inside that object or it has been assembled in some way later on. Okay? I have no way to say that. The only thing that I can say is that, for example, in the most massive clusters, like 47 Tychoon Centauri, you do see a difference in the distribution of the stars. Okay, but this is what is predicted, for example, in the scenario of AGB, intermediate AGB star formation. I can't say more than that.
That's very good. Our next talk is on photometric surveys of the white belt.